Where did you come from, baby? How did you know I needed you? How did you know I needed you so badly? How did you know I'd give my heart gladly? Yesterday, I was one of the lonely people. Now you're lying close to me, making love to me. I believe in miracles. Where you from? You sexy thing, you. I believe in miracles. Since you came along, you sexy thing. Where did you come from, angel? How did you know I'd be the one? Did you know you're everything I prayed for? Did you know every night and day for? Every day, needing love and satisfaction. Now you're lying next to me, giving it to me. I believe in miracles. Where you from?
Hello everyone, you can go ahead and put your earphones on now. Hello, welcome. This is Advanced Serverless Workflow Patterns and Best Practices, or DOP405. My name's Benjamin Smith, and I'm a Principal Developer Advocate for Serverless, part of the Serverless product team. And I have a lot to talk about in this next 45 minutes. But before I jump into the content, I want to give you a single landing page to dive in deeper in some of the content I'm going to be talking about. So here you have example templates that you can deploy. You have some really good workshops, lots and lots of code samples, videos, and blog posts. I'll put this slide up again at the very end of the talk for anyone that wasn't quick enough to catch it. But let's move into it. So this talk is all about helping you use step functions to deliver more value to your customers, to help you build serverless applications that are reliable and resilient to faults and failures, that are super scalable, hopefully simple to build, simple to reason about, and to be able to do this as quickly as possible. Building serverless applications is difficult. It's a whole new set of challenges, especially if you move from a more traditional way of building. And I like to think of serverless as a spectrum or as a pyramid of managed services, where at the bottom of that pyramid, you have these services which are maybe not serverless, which are really manual. Things like EC2, where you can throw up your code and build pretty much anything you like, but it's on you to manage that service and all the infrastructure that it relies upon. And as you move up this pyramid, the services become more and more managed. At the top of the pyramid is things like Lambda for compute, API Gateway for endpoints. You have DynamoDB for data. You have SQS for queues. You have step functions for orchestration. And each one of these services is specifically designed to offer a specific functionality. So the problem is that when you're building serverless applications that are relying on this managed approach, you're often building applications that consist of multiple services, right? It's not just going to be one Lambda function or one SQS queue. It's often spread out across hundreds or thousands of resources, sometimes across many different regions in your AWS account. So the challenge then becomes is when your application is relying on all of these managed services, working together, sharing data with APIs and events and queues and topics, how do you then understand how your application is actually held together? How do you track, visualize, and inspect the data as it passes through your application? How do you create common architectural patterns when it's a decoupled, serverless, asynchronous application? And my promise to you by the end of this talk is that I'll give you a number of patterns that you could go ahead and implement, a number of best practices. I'll talk a lot about cost optimization, specifically with using step functions. And I hope you'll then be able to go away and implement some of these ideas. Now, step functions is different in some respects to some of these other services. I think of it as the one service to rule them all, in that it allows you to orchestrate all of those other managed services into serverless, scalable workflows. Here's an example of the Step Functions Workflow Studio, which is a tool that's available in the AWS Management Console that allows you to build your workflows with a drag and drop interface. So here I'm selecting from a list of actions on the left, things like invoking a Lambda function, getting an item from a DynamoDB table, emitting an event onto EventBridge. And I'm dragging that into my design view. And I'm positioning it with choice, if statements. I'm allowed to add parallel branches. I can add dynamic map states. And then I can double click into each one of these actions and configure it with the editable form on the right. I can also export my workflow as code. It's a syntax called ASL. Looks a bit like JSON. I can commit that to my Git repositories. I can share that with the other developers in my organization. I can automate the build pipeline. And I can add it to my infrastructure as code templates. Now, Step Functions is pay per use. It scales automatically. It's right at the top of that pyramid of serverless managed services. One of the main components that it has is this built-in error handling for catching and retrying different states. Now, it integrates natively with over 220 other AWS services. And it does that by using that service's SDK directly from the Step Function substrate. So it's not spinning up a Lambda function under the hood in order to invoke that SDK action. It's actually doing that directly for you, so you don't incur any cold starts or invocation costs in that sense. So it actually has access to over 11,000 actions that you can drag in and organize as a workflow. Excuse me. Now, I like to say that you should start building with step functions in your next serverless application. Step functions first. I would almost go as far as to say step functions always, almost always. And I want to exemplify this with a really simple little microservice use case, which is the most common dead end that I see customers hitting all the time when they get started with building serverless applications. I would say 4 in 5 customers that I speak to about building in serverless have experienced this in some way or another. So let's go back to my first day as a serverless developer. I'm going to start with Lambda because I'm a developer. I'm like code. I'm familiar with code. I'm comfortable with it. And I'm just going to get an item from a DynamoDB table. So I'm probably going to start at the docs and learn about Lambda, the event-driven model. And I'm going to realize that I need to use an SDK in order to interact with DynamoDB. So I'm going to bring in my AWS SDK for DynamoDB, and I'm going to bring in the .client library. This will help me marshal and unmarshal my data, my JSON, to and from DynamoDB. Then I'm going to set up my params object for my SDK call, things like the table name, the partition key, the sort key. Then I'm going to set up my query items function, right? I'm going to create a try-catch block. I'm going to promisify the call using the .client to get an item from DynamoDB using the parameter that I set up, and I'm going to catch and return any errors. And then finally, I'm going to learn all about the event handler, what the event object is, what the context object is, what the difference between those two things are in Lambda. I'm going to stringify the response because that's what I need to do with Lambda. I'm going to use a async await query to call my query items function, and I'm going to return any errors. And there, in 20 lines of code, I've got an item from a DynamoDB table. Let's see how I could do that exact same workload, just as cost efficiently and just as performant using a step functions workflow. Ready? OK. Done. I just drag in the get items from step functions, right? I still have to configure the params object, but essentially these are 2 examples of exactly the same workload. Now, with step functions, I can still configure my retries. I can still configure and to catch any errors and send them downstream to a dead letter queue. Now, this isn't just how it looks like in a PowerPoint diagram. This is how it looks in the service, right? So I'm a busy developer. I'm context switching. I'm doing other things. I'm getting interrupted all the time. Which one of these 2 versions am I going to find easier to come back to in a day, a week, or a month's time and continue building with? For most people, it's going to be the workflow version. Now, let's say I go with my workflow version. and I start sending executions to my workflow. Now with step functions, I have a single pane of glass to see all of the failed executions, all of the successful executions, and I can drill down into each one of those executions and see where it failed, see what the error message was, see exactly at which step or which state it failed. Now these are things that are really difficult to do with serverless applications that are spread across multiple resources. I'm sure many of you here have spent a lot of time trawling through CloudWatch logs, trying to find where the error happened in various different log groups. With step functions, this is all part of the service. It's baked in for you. What I can also do with step functions is I can double click on each individual state and look at what the data looked like before it entered the state and what it looked like when it exited the state. So I can track my data for each individual execution. Excuse me. Now let's say I went with the Lambda model because I'm more familiar with code. And I'm happy with it because my Lambda function is scaling in response to requests, right? So it's scaling up and down for my spiky workload traffic that I needed. And I get a request from the business for this little tiny microservice to start doing more things. Now I want it to create, update, and delete things in my DynamoDB table as well. I want to access it from the internet. So I put it behind an API gateway endpoint, and I route all traffic to my Lambda function. Then in my Lambda function, I need some logic to decide which one of those actions to perform based on the API call, right? Based on the method or the query parameters, whatever that may be. So that's extra code just for routing. Then I need to configure my Lambda function with the correct security IAM permissions in order to do a create or an update or a delete on DynamoDB. So this is quite a loosely permissed Lambda function already. The more things I add to it, the more this Lambda function is allowed to do. I also have to configure the memory, the timeout allocations, and these are things that affect both the performance and the cost of running this Lambda function. And it will have that configuration regardless of which one of these actions it needs to run. So what many people at AWS might tell you to do is to split this out, right, into multiple functions, each one responsible for a discrete action, whether that's create, update, or delete. This is a good step. We've got some gains here because what we've done is we've taken that routing logic out of our one big Lambda function and we've moved that into the config of API gateway. What we've also done is we have permissions for each one of these Lambda functions that are unique to that function. So my create function, its only purpose in life is to create items on DynamoDB. That's all it's able to do. And the same for update and delete. And the same for the timeout and the performance allocations as well. So what's the issue? Well, now we have 3 separate Lambda functions, each with very similar but slightly different lines of code. We have 60 lines of code now instead. And as my application grows and grows, this becomes more and more difficult to manage and orchestrate. Here's the first pattern I want to show you. It's a REST CRUD API that doesn't have any Lambda at all. It goes from API gateway directly to step functions. And what this does is I can still route all valid requests to my workflow. The first step in my workflow is a choice state, which decides which one of these actions to run based on that inbound request, get, put, post, or patch. And then it uses the DynamoDB SDK to perform that action directly. So there's no Lambda cold start times, there's no Lambda invocation costs. This is just as performant and just as cost effective if you run it in a certain way, which I'll explain in a moment. The reason we came up with this pattern is from a real application. It's called Serverless Espresso. Maybe people have seen or heard of this Serverless Espresso application. I think it's been at the Amsterdam Summit before. And this was a little demo application built by my team to allow you to order a cup of coffee from your mobile phone at an event, such as reInvent or a summit. And it has this little microservice in it called the Order Manager Service, which is just a REST CRUD API that goes from API Gateway to Lambda and other services as well, and to DynamoDB. And we had all those issues that I mentioned before, right? Tightly coupled code base, slower release cadence. We had some lag issues because this was a real-time application running at reInvent, servicing hundreds of orders across a couple of minutes, right? We had some issues with this. We found it really difficult to debug this while it was running in production. Impossible, in fact. We limped through that year's reInvent. we went back to the drawing board for this microservice, and we rebuilt that microservice as a workflow. And what you'll notice, there's only one Lambda function in this new workflow, and that Lambda function is doing some compute, right? It's not just transforming and moving data from one service to the next. It's actually calculating something, which is a much more sensible use of Lambda. Now, we chose to run that as an express workflow. And this choice is very important for reasons that I want to go into next. When you're building with step functions, you have two modes that you can run your workflow as. That's express or standard. And this is all about understanding, when you're building with serverless applications that are using managed services, there's always a cost associated with using a managed service. And there's so many different variations on the different features available to you with those different managed services, right? There's many overlaps. There's lots of different ways to do one thing. So as developers, I think it's our responsibility to understand the cost model for some of these services that we're using so we can get the most out of them. So this is how it works with step functions, standard, and express. Standard workflows can run for up to 1 year, really long-lasting. They have an asynchronous execution mode. So you start your standard workflow, you won't hear back from the response unless you query that by some other means. And they have an exactly once execution model. Express workflows have a much higher throughput, so they transition through those states much more quickly. They have a totally different billing model, which I'll explain next. They have an at least once execution, so that means you can get duplicate invocations with the same input. So you have to make sure your express workflows are idempotent, which means if you run it with the same input, it'll always produce the same results. They can be both asynchronous and synchronous. So for example, you can call an express workflow from API Gateway. API Gateway can wait around here for up to 29 seconds for the response. My express workflow will run, send the response back to API Gateway, and then back on to the requester, the nice synchronous loop that you might want sometimes. Here's the important bit. They can only run for up to 5 minutes. So standard workflows, 1 year, express workflows, 5 minutes. I want to show you why it's important to pick one or the other with a close to real life example. So this is a workflow that simulates a common e-commerce workflow. It does things like approve an order request using SQS, then it polls a DynamoDB table to check that the order has actually been approved, and then it notifies that that order's been made, and then it waits to check that the payment's been processed before running a series of idempotent Lambda functions to update inventory and data warehousing and things like that. I saved this workflow as an express and as a standard workflow and ran it 1,000 times with the same inputs for both express and standard. And I want to show you the results because I think it's a nice way to explain the difference. So run 1,000 times. This cost 42 cents as a standard workflow and 1 cent as an express workflow. Exactly the same inputs, exactly the same workflow, just run in 2 different modes, right? And I want to dive into why that is. Standard workflows cost is all about how many state transitions in your workflow, right? And this is the original step functions type. This is why there has been talk in the past of step functions being expensive because it's all based on the number of state transitions. And you pay $0.025 for every 1,000 state transitions. So with my workflow here, on the happy path, there are how many state transitions? I believe 17. There we go, 17 state transitions. I run it 1,000 times, so that's how I get my 42 cents. There's an asterisk because it does have a free tier, but I'm going to assume we've gone past that free tier for now. Then my express workflow, very different. Doesn't really matter how many state transitions it has. It's all about how long the workflow takes to complete, right? The amount of time to the nearest 100 milliseconds that it takes to execute at a given memory allocation. So to work out the cost of my express workflows, I need to know how long it took and what memory allocation it used. Now, the memory allocation is not something you can configure like you can with Lambda. It's configured for you based on the input payload size and the definition size of your workflow. And this is taken from the AWS pricing page, it goes up in 64 megabyte increments. This is a very small workflow with a very small input payload. So it's using this number here. This is the price per 100 milliseconds for the first 1,000 GB hours, right? I put that back into my formula. This workflow takes on average 11.3 seconds to complete. I run it 1,000 times, and that's how I get my final result of $0.01. So if you extrapolate this out, that was just 1,000 executions. Imagine I'm running this millions of times. The difference starts to separate very quickly, right? I don't know if you can, yeah, you can see that. They start to separate very quickly, and it becomes really apparent that I should definitely run this as an express workflow and not a standard workflow. And I think everything you see in the docs will probably be an example of a standard workflow where you should default to express workflow, in my opinion. When would you ever choose to use a standard workflow? That should be the question you're asking yourselves. And the answer is if your workload does take more than 5 minutes, right? Then you can't run it as an express workflow or it'll time out. If you need these special patterns like task token or sync, then you have to use a standard workflow. And if you do require that exactly once guarantee, then again, you'll need a standard workflow. But here's something you can try. How about both in the same workload, right? You can get the benefits of both. And this is the next pattern I want to show you, and this is the nesting pattern. So you have a parent standard workflow that can run for up to 1 year that builds based on state transitions, and within that, you call a child express workflow that's fast, more performant, and based on the cost based on the duration. So let's go back to this example. Imagine this polling loop here sometimes took more than 5 minutes. Imagine there was a human involved in that, and maybe they don't get back to that within 5 minutes all the time. What could I do to this workflow? That means I have to run it as a standard workflow now. What could I do? Well, the first thing, the low-hanging fruit here, is to take those idempotent Lambda functions and save them as a new separate express workflow and call that synchronously with a start execution command from my parent standard workflow. So now I've got two workflows, one kind of embedded within the other, and you can see how that affects the overall cost of my application, right? My standard workflow now has only 14 state transitions, so it costs just 30 cents. My little child express workflow finishes in 1.3 seconds. The overall cost of that is so insignificant, it doesn't really make any difference when we add them together. So now I have this workload that can now run for up to 1 year, and it's costing me just 30 cents to run, down from 42. The thing to remember when you're trying to optimize for cost with step functions is if you're using a standard workflow, you want to reduce the number of state transitions. If you're using an express workflow, you want to reduce the amount of time your workflow takes to complete or the amount of memory that it needs in order to complete. They're the three key factors across step functions. But that's just the cost of the orchestration piece, right? That's just your step functions cost. I want to point out that there's an overall cost of your application, which is about the managed services that you're invoking within your workflow. So here's a really simple workflow. The first cost here is DynamoDB, get item. That's taking up read capacity units. That's a DynamoDB cost. Then I have my first state transition. Then I have a Lambda invocation cost. Then I have my next state transition. And then I have my event bridge cost. Again, that's another separate cost to step functions. So another thing you can try and do is reduce the reliance on managed services where you don't need it. What do I mean by that? Well, step functions has these helper methods built in called intrinsics. And these allow you to perform simple data transformations to reduce the reliance on maybe something like a Lambda function. So this can help you manipulate arrays, JSON objects. It's good for encoding and decoding data, simple string and math operations. You can even generate unique IDs as well. I'm going to give you one example. So up until recently, the most requested intrinsic function was to generate a unique ID. And this is what people had to do before we introduced this intrinsic. They'd have to have a whole Lambda function that was spun up, that would have to pull in some secure library to generate that unique ID. So here's 4 lines of code just to return a unique ID and a whole Lambda invocation cost associated with that. If I can produce the exact same results using intrinsics, then I should do that, right? So here's how I do that using step functions. It's states.uuid. I have no invocation delays, there's no cold start time, there's no invocation cost, there's no code to manage. This can just be part of a state that already exists. There's one more thing I want to show you with this example here. We have a polling loop here because this is an asynchronous workload, right? I don't know when this is going to complete, so I need to wait a certain amount of time and check back, and then wait a certain amount of time and check back, and there's another one down here. Most commonly, I see people using polling to understand when an asynchronous task is complete. And I think that's because it's the easiest way to do it, right? It's simple to implement. I know it's simple to implement. I have a story, in fact. I think we have long. I live on the south coast of England in a little city called Brighton. And last year, I decided to take my daughter on a day trip to France on the boat from a lovely town called Newhaven to France in a town called Dieppe. We got the train to the boat, we got on the boat. The first question my daughter asked me when the boat started moving is, "Dad, how long is this going to take?" If anyone's interested, 5 hours. So she proceeded to poll me for status updates every 5 to 10 minutes to check our journey, right? Check how it was going. Really annoying, really chatty, really expensive, had to keep coming up with ways to keep her entertained. It's the same with your workflows, in a sense, because every time you go around this polling loop, you're having 3 state transitions, and that's an additional cost every time you go around. Now, what you could do is change the wait time, right? So you could wait longer before you ask, but that would mean me and my daughter could be sat on the boat for half an hour before we realize that we're there. So that doesn't really work either. A better method, both for your workflows and for my sanity, would be to use a callback method. So this would be like us getting on the boat, and she says to me, "Dad, can you let me know when we get there?" And I'll say, "Sure thing, kid," and then we can just look at our phones for the next 5 hours like everybody else. You can do the same thing with step functions. It's called the callback pattern. I'm going to do it and explain that here. There's 2 patterns when I build with step functions that I always implement either one or the other, or both. This is the first one. It's the callback pattern, or the emit and wait. So this allows you to orchestrate a series of events in a particular order, pausing until each event is complete. Here's an example of how you can implement it arbitrarily, right? So let's say I have milestone 1, and I'm going to use step functions partner in crime here. It's like the Batman if step functions is Robin, and that's Amazon Event Bridge. They work so well together. So I'm going to emit an event for milestone 1, and along with that event, I'm going to tell step functions to generate this unique task token. What that means is that step functions will wait here until it hears back with that task token. And you don't pay for the wait time because there's no state transitions. You can wait for up to 1 year, right? I save that task token somewhere, like a DynamoDB table, and when milestone 1 is finished doing whatever it needs to do, I grab that task token back and I send it back to my workflow and say, here it is, that's a success. You can move on to milestone 2 now, where the pattern resumes, and off we go again. Now, if I don't want to wait for 1 year for every milestone, which is reasonable, I can set a heartbeat or a timeout. Once that amount of time is reached, I can catch that, and my workflow will then take a different path. So, back to this e-commerce example, I'm going to cut out those 2 polling loops, and in the step that precedes them, I'm going to add this wait for task token syntax, this ASL syntax. This is what tells step functions you're going to stop here and emit a task token, and you're going to wait until you hear back with that task token. So now the overall cost of my workflow, because I'm not going around this polling loop, reduces again. I now only have 8 state transitions on the happy path. It now only costs me 20 cents, and it can still run for up to 1 year. And I haven't even started adding intrinsics to this because we need to move on and talk about some other stuff. I like giving real examples of things that the team has built to demonstrate stuff. And this is another example that the team built. It's an application called Serverless Video. And it's an application that we ran at reInvent in December, just gone, that allows you to live stream from your mobile phone. And we would interview speakers and customers and partners, little short videos at the booth, and live stream this, and people would kind of share the event as they were going through reInvent. What then happened is when the live stream or that broadcast ended, that video file would go through a post-processing workflow that would add all sorts of valuable information for that video to be available to watch on demand. Here's a small example of what happened in post-processing using step functions, right? We would use Lambda to convert the small TS files, the streaming files, to a single downloadable MP4 file. We passed that MP4 file to Amazon Recognition to make sure that the imagery in the video is appropriate. We would then pass that on to Amazon Transcribe to work out what was said in the video, how many speakers there were, before passing the transcription onto Amazon Bedrock, along with some prompts to generate titles, tags, and categories to help store that video for the future to be playback on demand. We were so happy with this idea, we decided to go out to all of the serverless speakers at reInvent and challenge them to build a plugin based on their talk, right? To build an event-driven plugin. And we had all sorts of interesting things that were submitted back, things for moderation, for leaderboards, for translations. We had, I think, 52 plugins that were submitted to us. So now we created a new problem, right? We had to somehow orchestrate these plugins without really knowing how many we would have when we went live. Some plugins had to depend on others, some had to run before others ran. We needed to know what to do if some failed or timed out. We needed to know that they would even work before we deployed them into our production account. Step functions and emit and wait to the rescue for this whole workload. We created a series of arbitrary events. We called them pre-validate, post-validate, pre-metadata, and post-metadata. And we said to our plugin developers, these are the types of plugins that you should subscribe for each one of these events. And here's an example of midway through that workflow, right? The pre-metadata event. It emits an event along with a task token to one of our many plugins, the transcription plugin. Transcription plugin takes that payload, which also contains the MP4 S3 URL. It runs transcribed against it, saves the transcription back to S3, and then it gives the task token back to the pre-metadata workflow. All the other plugins, we wait for them to come back. I think we wait for up to 3 minutes. When they're all returned, we go ahead and the workflow moves on to the post-metadata event. Now, the post-metadata event, one of the plugins is this generate title using Bedrock. And that has that pointer to that transcription file. We provide a prompt along with that to say, generate us a nice title along with the transcript. And then that title is sent back to the workflow. And this allowed us to create a workflow where we didn't really know what plugins would be submitted, how many would be submitted. We could deploy and tear down any plugin that we wanted, and it would never affect our application because it was event-driven, with events calling out to these plugins to start and stop, and then our workflow orchestrating the order assurance of each of these plugins. Really nice pattern that we were pretty happy with. This handsome chap is Werner Vogels. He's the CTO of Amazon. He's well known as having been quoted that everything fails all the time. Step functions is great for managing failures. Here's a very commonly known pattern in computer architecture. It's called the saga pattern. And this allows you to roll back a series of sequential events in the order in which they occurred. And I think it's a really nice visual way of implementing the saga pattern, right? Let's say in this example is a holiday booking system where I book a hotel, I book a flight, I book a car. This is the nice, happy path. If the first step fails, I can catch that failure and unroll that, roll that back. If the first step passes but the next step fails, well, I can capture that and then kind of waterfall down and roll back sequentially. So I think you can see visually right away how this can work to roll back a series of events in the correct order. Another common pattern is the circuit breaker. Excuse me. So here I use this pattern to prevent my application from calling a downstream service that I know to be broken or unhealthy, right? This could be something, maybe you have a traditional app or an on-prem app that doesn't scale in quite as bursty a way as your Step Functions workflows does, and you need to protect that. Well, you can do that using the circuit breaker. What you have to do is maintain the overall state of your application somewhere, for example, DynamoDB, and for each execution, you query that state. Is my circuit open or closed? If it's closed, that's good. I'll go ahead and I'll run whatever needs to be run. In this little example, it's a Lambda function, and I exit. The next execution comes in, it does the same query. Circuit's closed, okay, we'll run Lambda. This time, Lambda fails. I capture the failure, I open the circuit so that next time my workflow is triggered, I am not invoking Lambda, I'm not incurring those costs, I can go down some other escalation path instead. Step functions at scale. There's loads of ways of building super scalable workflows using step functions. I could do a whole topic on this, but I'm just going to cover what I think is the most important things, right? The first thing to know is about parallel invocations. This is the same workflow definition where you're sending different inputs to it. And the thing to know is that they're kind of single-threaded in that none of them know about each other. So if one fails, it shouldn't affect the others. Then you've got something called the parallel state. So this executes a fixed number of branches in parallel. They all get the same input. So in this example, it's a user ID. The user ID is given. One of them looks up the zip. The other one looks up the number. Once they're both completed, and only once they've both completed, the result is then sent as a result array to the final state. And these branches will run at the same time, right? They'll run in parallel. So you can do lots of things together to reduce the amount of time your workflow is running for. Here's a really good tip, a really interesting way of using the parallel state for any geeks that are already using step functions a lot. Sometimes you might have a variable at the top of your workflow that you need to pass all the way down to the bottom. And you'll need to use ASL to push this down all the way to the bottom, right? And this is really buggy and easy to make a mistake or a typo, easy to go wrong. Because there's no concept of a global variable yet in step functions. You can use this pattern, data preserver. So you use a parallel step where one branch kind of holds in local memory all of those variables that you need at the end of your workflow, and the other branch performs the actual processing, right? And at the end, so here's a task token that I'm holding, and at the end, when that parallel step exits, I have both my task token and the result from the other branch. So it's a nice little hack, really, but I was pretty happy with it. Then you have something called dynamic parallelism. Now, this is a bit like executing a sub-workflow within your workflow, where you don't know, at the time of running, you don't know the inputs that will be handed to that sub-workflow. It gets handed to that map state. Dynamic parallelism uses the map state. It gets handed to it as an array of items, and you can tell it to do each item single-threaded, one at a time, or all together up to a concurrency of 40, right? And here's where you start to get some really powerful patterns. So the first one I want to show you is the fan-out pattern. A couple years ago, my team built an application called, what's it called? Serverless Land. It's a website that aggregates all the serverless content from AWS into one place. And when we first built it, it was just aggregating blog posts. And the first thing it did was use a workflow to populate, and it would scan an RSS feed for all the blog posts. This would run on a schedule each day. Scan the RSS feeds for all the new blog posts from the last 24 hours. That would produce an array of URLs. We would then send that to this map state, which would go ahead and scrape additional data from those blog posts, right? Produce an object like this for each post. We would then send that object to another Lambda function that would write this to GitHub for each blog post before finally triggering a new build to go out onto S3. And that's how we would keep up to date this aggregation website. We actually improved it by using the fan-out, fan-in, or the scatter-gather, by moving that save to GitHub step outside of our map state. Here's what I mean, right? So we scan all of our blog posts, we scrape the metadata concurrently or in parallel, and then we have an array of metadata, and we just do one state to save to GitHub rather than doing that inside our map state. This is a standard workflow, so we want to reduce the number of state transitions, so we move that outside of our map state. Customers wanted more concurrency. They wanted more parallelism than 40. What they were doing is they were embedding map states within map states, which was kind of clever, but really difficult. So we created something called the distributed map state. This is similar, but it gives you a concurrency of 10,000. So we went from 40 to 10,000 in one release. And this works really nicely with S3. So you can point it at an S3 bucket and say for each item in this S3 bucket, run your steps. Or you can point it at an S3 object, and you can say for each line in this CSV file or this JSON file, run the distributed map state. Here's a really silly example, really, but I think also a really powerful example is this serverless GIF generator. So this allows me to provide to the workflow an MP4 file where I want to create a GIF animation for every 30 seconds for something like a timeline scrubbing web application. So the first thing it does is it runs, and it has the name of the MP4 file and the name of the bucket. It uses Lambda and FFmpeg to calculate how many GIF animations it will need to create based on the length of that movie, and it produces a metadata file for each individual GIF animation, and it saves that file to S3. Then I enter my distributed map state. Now here's the magic bit, really. It doesn't matter if my original MP4 file was 5 minutes or 5 hours, because I'm going to create each GIF animation at the same time, concurrently, right? This is the other super powerful pattern that I wanted to show you. The idea, and I think this is the fundamental point of using serverless, right, is that you're able to break down large workloads into smaller and smaller pieces and use the economies of scale that you have available to you at AWS to run those small pieces all at the same time and then aggregate the results. This is the other powerful pattern, is this and the emit and wait. Used together, you can create so many different variations of super scalable and cost-performant applications. If you want to see more patterns, and I mean hundreds of more patterns, this is a great resource. It's s12d.com/workflows. And here you have a number of patterns that were uploaded by people at AWS, by customers, by partners, to do any number of different things. You can see visually what each workflow does. You can inspect the infrastructure as code template. We have SAM, Terraform, CDK, and CloudFormation. You can even look at the ASL that defines that workflow to help you debug any problems that you're having. Here's that final landing page that I promised I'd show again at the beginning of the talk, where you can dive deeper into all the different things that I've been discussing in the last 42 minutes. Downloadable templates, blog posts, videos. There's 2 very good workshops. One of them helps you to build serverless Espresso from scratch. The other one is a Step Functions workshop that just takes you through all the different functionality of Step Functions. I believe you can redeem a free 7-day trial of Skills Builder as well. I'm sure you've seen that on every other talk that you've been to today. If you like this session, please give it a 5 so we can talk more about this kind of thing, cost optimization and patterns in the future. And with that, I'll say thank you so much for your time, and I hope you enjoy the rest of the summit. Thank you.